Hello everyone, thank you for attending my presentation today. The topic is studies of low and intermediate temperature oxidation of propane up to 100 atm in a supercritical pressure tested reactor. My name is Zhao. I'm currently an assistant professor from Peking University. My collaborators in these presentations are Dr. Chao Yan, Dr. Guohui Song, Dr. Ziyu Wang, and Professor Yigong Ju from the Department of Mechanical and Aerospace Engineering of Princeton University. So first, I will briefly talk about the background of this presentation. I usually use this typical of figures to show the general engine operation regimes, which is the equality ratio versus temperature figure. And from this figure, we can see the spark ignition happens around 2600 kelvins and at equality ratio around 1, where the NOx formation is high. And here it shows the optical observation of the gasoline engine operation. And the generally the conventional diesel engine operates along the orange line. On one hand side, the soot formation is high. On the other hand side, the NOx formation is high. We can also see the optical operation of the diesel engines here. And to reduce the NOx formation and the soot formations, we have to operate the engines at in the blue region, where it's usually called the HCCI regime, the homogeneous charge compression ignition regime, where the temperature is relatively low. It's between 1400 Kelvin to 2000 Kelvins, and the equality ratio below to 1. It's called ultralean combustion, ultralean conditions, and we can see the engine operations in this video. And to further accelerate the oxidation or combustion, a higher temperature is favorable for this engine operation. And to summarize the characteristic of this regime, so it's called ultimate combustion. So among the ultimate combustion regime, the supercritical combustion receives increasing attention due to its higher thermodynamic efficiency and low emissions. However, supercritical combustion possesses a lot of challenges. For example, the intermolecular force cannot be ignited at high pressures, and the transport and the thermal chemistry has to be corrected at the supercritical conditions, and the reaction rates also need to be updated by including the intermolecular force. And unfortunately, there are limited experimental approaches to study the supercritical combustion kinetics. So here I summarize the experimental setups to study the reaction kinetics. So generally, flow reactor and the GSR can only operate at low pressures, and even shock tube can cover the low pressure and high pressure kinetic studies. It's usually operated for studying the high temperature chemistry or high and intermediate temperature chemistries of fuels. Therefore, and the real engines usually operates along the dotted line, the two dotted line. So for most parts of the dotted line, it cannot be covered by the current experimental approaches. Therefore, we have two questions. First, can we design a new reaction system for the supercritical kinetic study? The second, is the reaction system able to capture the low and high temperature chemistries of the fuels relative to the engine operations? The answer is yes. So we recently developed a supercritical pressure adjusted reactor (SPGSR), which can be operated around from 10 atm to 200 atms, and is operated in this pink rectangular. You can see that it can cover the most part of the real engine operations. Moreover, high-pressure kinetic data are very rare for the supercritical combustion study. For some fuels, the low-temperature chemistry has not been covered at high pressures, and for some fuels, NTC behavior is not well captured due to large uncertainty. And for some fields, NTC behavior is even not captured. Here are two examples. The first one is the ignition delay time versus the temperature. For unbuilt, we can see the pressure, the highest pressure here is 30 atm, and a higher pressure is ignition delay time data is not available in literatures. And the second example is propane oxidation at 100 atms. Even though the pressure is higher, is very high for starting the supercritical combustion. However, the NTC behavior is not captured, or is not clearly captured in this flow reactor experiment. Therefore, we have a question. So what is the coupling between the low temperature chemistry and the supercritical effect, and how does the NTC behave at supercritical conditions? So with these questions in mind, the objective of this presentation is to study the low temperature chemistry of propane at engine relevant conditions by using a normal supercritical pressure reaction system, SPGS, and second, to understand the negative temperature coefficient NTC behavior at supercritical conditions. Then I will briefly talk about the experiment. The SPGSR is the first GSR above 100 atm and is capable for the low and high temperature supercritical kinetic study. And the right figure shows the general schematic of the design of the SPGSR, which has been published in the last symposium for studying the unbuilt oxidation at 100 atm. So we can see that the reactor is very small with a volume of 0.4 milliliter. We can see that the diameter of the reactor is even smaller than a coin, and it has 8 jets with a jet diameter of 0.2 millimeter, and the resting time of the reaction of the system is 0.1 to 0.5 seconds, which is very relevant to the real engine operations. Even though it's very small, it has a better jet arrangement with less vortex. For experimental conditions, it has 4 cases. For case 1 is in the lean case at pressure of 10 atm. For case 2 is also in the lean case, but the pressure is 100 atm. For case 3, all the conditions are the same to case 2, but in case 3 it has 20% CO2 additions here. And for case 4, so it's in the rich case with a pressure of 100 atm, and the resting time is in this range, and the temperature is from 500 Kelvin to 1000 Kelvin. And the 4 kinetic models, the Aramco Mach 3, ULCC Mach, Hashimi Mach, and the Polymer Mach, are used in this study. As to the results at 10 atm, these 4 figures show the mole fraction of propane, CO2, formaldehyde, and ethylene in the oxidation of propane at 10 atm for the case 1. So basically, the low temperature chemistry of propane has not been observed at 10 atm in this case under these experimental conditions. And generally, the Aramco Mach, Hashimi Mach, and the Polymer Mach captures the oxidation in experiment reasonably well, while the ULCC Mach cannot capture the oxidation and predicts the major products and intermediates well. In contrast, the experiments at 100 atm shows a very different picture. So the temperature evolution of propane in the propane oxidation without the CO2 additions at fueling conditions in case 2, and with 20% CO2 additions at the fueling condition in case 3 at 100 atm is shown in this figure. So you can see the black and the hollow series presents the experiment with and without the CO2 additions. And you can see that there is a clear low temperature chemistry curve observed with a weak and flat NTC behavior. And comparing the experiment with and without the CO2, it shows that the CO2 possesses limited impact into the propane oxidation. So as to the model simulation, we can see that. So the ULCC Mach doesn't show low temperature chemistries in this in this experiment and simulation study. And Hashimi Mac shows a very limited and negligible low temperature chemistry. And as to polymer Mac and Aramco Mac, they generally exhibit the low temperature chemistry and shows the flat and weak NTC behavior. However, these two models still predict the oxidation at the NTC region. So for the rich case, so the general characteristics of the experiment and the model simulations are very close to the lean case. Therefore, we mainly focus on the lean case analysis. At 10 atm, propane is the major intermediate in the propane oxidation, and more than 90% of propane is formed to propane and follows the propane high temperature chemistry to form CO and CO2. That explains the non-observation of low temperature chemistry of propane at 10 atms in case 1. But for the pathway analysis at 100 atm, so the decomposition of free radicals to propane is negligible instead. So the O2 formation from free radicals with O2 addition becomes more important. And at 100 atm, the O2 chemistry dominates the reaction path throughout P1. The O2 isomerization reaction to QH, and P2, so the O2 decomposition reaction to propane and HO2, so which is the major reaction in the intermediate temperature chemistry. And at high pressures, we have to see that the intermediate temperature chemistry is shifted to a lower temperature, making this reaction dominate in the O2 chemistry in the NTC region. And also P3 appears at 100 atms due to the increase of HO2 and formaldehyde molecules at high pressures. And therefore, this reaction, the O2 plus formaldehyde and HO2, becomes more important at 100 atms. We also performed the sensitivity analysis for propane at the fueling conditions in case 2 at 100 atms and 720 kelvins by using the Aramco Mac. The sensitive reactions are the H abstraction reactions from propane and the O2 competing reactions through P1, P2, and P3. And another important category of the sensitive reactions are the formaldehyde and HCO chemistries. And the appearance of sensitive reactions in P1 to P3 pathways confirms the importance of P1 to P3 in the pathway analysis above. Due to the limit of the time, I don't go to details of the speciation of the important intermediate and product species for the lean and rich case. But generally, so the low and the intermediate temperature oxidation peaks against the temperature began to merge to a single peak as the NTC behavior is suppressed. So the Aramco Mac and the polymer Mac generally captures the oxidation characteristics of the major products and intermediates in the experiments correctly, and predicts their concentrations in the NTC region significantly. To conclude this presentation, there are 3 sets of takeaway messages. First, so as SPGSR is used for studying supercritical combustion chemistry, like propane. And second, propane oxidation at 100 bar. So we observed a weak NTC behavior. And the second, both the low and the intermediate temperature chemistries are controlled by the O2 reaction pathways. Third, so the models predicts the oxidation in the NTC region. And the next, so the O2 plus formaldehyde and HO2 reactions appears at high pressures in this experiment and the modeling study. So beyond this conclusion, we have an outlook. The left figure shows the experimental and simulation results of unbuilt oxidation at 100 atms in our last symposium presentation, and the right one is the figures in this presentation. We can see that for both propane and unbuilt models, so the end predicts the fuel oxidations at the NTC regime. Then we have a question. Does there exist large discrepancies in a series of pressure-dependent reactions in their low-temperature chemistries, especially at the NTC region at high pressures? To answer this question, we are performing ultra-high pressure fuel chemistry studies such as hydrogen, methane, methanol, propane, DME, and unbuilt. And we also perform the real fluid computations by using Worrell equation of state to understand the effects of thermodynamics, transport, chemical potential, and other effects on the real fluid simulations. So with the experimental and theoretical studies, so we would like to perform the hierarchical development of supercritical combustion chemistries. So the right figure is a typical combustion chemistry pathways of fuels at low, intermediate, and high temperatures. So we would like to develop a combustion chemistry structures of fuels at supercritical conditions as well. So questions are welcome to Professor Guangju and me. So thank you for listening in my presentation.